So, next we will discuss on this test pattern generation technique, but before going to the details of this test generation algorithm. So, we need to discuss about some of the theoretical foundations of this testing process. So, they are based on one Boolean operation which is known as Boolean difference operation. So, this circuit is implementing realizing the function f equal to x y plus y bar z. Okay. Now, suppose we are targeting the fault y stuck at 0. So, then the faulty function for the faulty circuit is f dash with which is a modified version of f with y equal to 0. Okay. So, if this modified circuit is f dash, then goal of the test generation is that under this faulty condition, this f x or f dash. So, this output should be equal to 1. That is, we have got this circuit. So, if we create another circuit which is f dash and run those two circuits simultaneously with this particular vector that we have found, and there is a hypothetical XOR gate at the output of which combines the outputs of these two copies of the function f and f dash, and this output is 1. So, we have to find a vector such that is f x or f dash equal to 1. Okay. So, this is determined by this Boolean difference operator. So, naturally f x or f dash will be equal to 1 if and only if f and f dash they are in opposing logic values. That is true, then only the XOR gate will be 1. So, any vector that can set f x or f dash equal to 1 is it can put opposite values to the f and f dash circuits. As a result, we can have this output detected, the XOR gate will be equal to XOR gate output will be equal to 1, and we can say that the fault is getting detected. So, we define this operator differential operator df dy is equal to f y equal to 1 XOR f y equal to 0. So, if we apply, so this is the function, this is the definition of this df dy. So, it is differentiation of function f with respect to variable y. So, it is equal to the function f with y set to 1 XORed with the function f with y set to 0. So, in this particular case, so if we do this thing, so to excite y equal to excite the fault y stuck at 0, one thing that is needed is first of all this line y should be equal to 1, and the remaining part will ensure that f y equal to 1 and f y equal to 0. So, these two functions they are XOR being 1 will ensure that the fault actually propagates. So, as we have seen in the test generation process, there are two parts. One part is to excite the fault and the second part is to propagate the fault. So, for exciting the fault, so we need the line to the particular point to be set to equal to the opposite of the fault that we are going to detect. So, since in this case we are going to detect y stuck at 0, so we would like to put y to be equal to 1. So, this is one condition to be satisfied, the y must be equal to 1. Second condition to be satisfied is the XOR of faulty and fault free circuits, they should be equal to 1. So, that is given by the differentiation of f with respect to y. So, f y equal to 1 XORed with f y equal to 0. Now, the function that we had was x y plus y bar z. The function f we had is x y or y bar z. Now, if we take these two cases, that is f with y equal to 1, f with y equal to 1. So, this function is x, and f with y equal to 0, this function is z. So, these two are XORed. So, you see in this expression that this y part is for putting this y line to 1, and then the remaining part is for the propagation, this XOR of these two. So, it is y and x XOR z. So, if you expand it, ultimately we get x y z bar and x bar y z. So, these are the two different test vectors that can be applied to check whether that particular fault has occurred or not. So, you see, for a quick check we can see that in both the cases y line has been set to 1. So, we are trying to check y equal to 0, y stuck at 0. So, it is putting y to be equal to 1. So, the excitation part is satisfied. Now, this x is 1 and z is 0. So, since x and y both are 1, so this fault free output is this fault free output is 1, and if the fault is present, then also this output will be 1. On the other hand, this y is coming here, so y, this line is 0 and z is 0, so this gate is 0, so you are getting a 1 here. But if you are having the fault, that is y is stuck at 0, then this AND gate output will be 0. So as a result, this will be you will get a 0 here, and this z line is 0. So z line, this line will be 0. So you will get a 0 at this point. So this way, this 0 that we had is propagating to the output. So that way it can detect this particular fault. So it can detect that y stuck at 0 fault by the first test pattern. So if you just try for the next one also, you will see that it is able to detect this particular fault y stuck at 0. So there is a more detailed example here. So in this particular circuit, suppose we are trying to check for this particular fault w stuck at 0. So previously y that we had taken, so y was a primary input. In this case, w is an internal line of the circuit. So for this internal line of the circuit, again we need to satisfy this condition. We need to excite that fault by setting w to 1, because we are trying to check for w stuck at 0. So we need to put w to 1, and then this propagation, which is df dw, should be equal to 1. So w and df dw, this whole thing should be equal to 1. So if you expand this, so we need to do this thing. So this so df dw, so we need to find out. So df dw, if you want to find out, then it is df dw is f with w equal to 1 XORed with f with w equal to 0. So if w equal to 1, then naturally this gate output is 1. So it is 1, and w equal to 0, so this puts the value to be equal to this xy. So this is coming here. So it is 1 XOR xy. So it is xy bar. So w and xy bar should be equal to 1. So we just expand it by De Morgan's law. So we get w x bar plus w y bar equal to 1. So this is the condition. Now w is given by y bar z. So if you substitute it here, so y bar z x bar plus y bar z y bar equal to 1. So x bar y bar z and y bar z should be equal to 1. So if you just further simplify it, we get y bar z equal to 1. So y bar z equal to 1. So x becomes a don't care. So we don't need, the test generation process need not assign any value to x. So value can be 0 or 1, but y should be 0 and z should be 1. So this is the test. These are the two test patterns to be applied for checking w stuck at 0. So in this way, for any circuit, any combinational circuit, you want to detect a particular fault. So we can do this thing. We can take that particular fault at that line, excite that particular fault by giving proper value to it, and then propagate it by taking the differential of the function with respect to that particular line. Another example, suppose we want to check z stuck at 0. So again the same, z df dz should be equal to 1. So df dz, if you that is given by z and f z equal to 1, f of z equal to 1 and f of z equal to 0. F of z equal to 1, if z is stuck at 1, so you see that this AND gate becomes a 2 input AND gate. So xy, and this z, if z is 0, then it is definitely 0. So z equal to 1 XOR z equal to 0, this part becomes 0. So this is xy. So this is xy XOR xy equal to 1. So xy XOR x is 0. So you see that we want z and 0 to be equal, which is not satisfiable. So if it is not satisfiable, naturally I cannot have any test pattern that can detect this particular fault, that z stuck at 0. So this becomes an untestable fault. The fault is untestable fault. So if we can detect all, as we have discussed previously, so if we can detect all the untestable faults in the circuit, then we can remove them from our consideration in the test generation process. So this is the theoretical way of finding a fault to be untestable. So in general, we can say that given a circuit with output f and the fault to be detected alpha stuck at some value v. So alpha is the signal line and v is the value stuck at 0 or stuck at 1, like that. the set of vectors that can detect this fault includes all vectors that satisfy this particular condition, alpha equal to v bar, the opposite of the fault that we have to excite. Okay. So, alpha must be equal to the opposite of the fault, alpha equal to v bar, and df d alpha should be equal to 1. So, this is the formula to be applied for generating the test patterns for the particular fault alpha stuck at v. Okay. In general, we do not need an entire set of vectors. The Boolean difference method that we have seen, the advantage is that it gives you all possible test patterns that can detect a particular fault, but it is not required. In many cases, we may be satisfied with having a single test pattern for a fault, or maybe a few test patterns for a particular fault. That depends on the application that we have, but in very few cases, so we will require all patterns that can detect a particular fault. So, that is generally not needed. So, rather than using Boolean difference that can obtain all vectors, so we can use some sort of branch and bound search technique to find one vector quickly, and then we can do this fault simulation to see what these vector which more faults this vector can detect, and then try out with the remaining faults, dropping all the detected faults from the set. So, this deterministic ATPG, it has got two goals: excite the target fault and then propagate the corresponding fault effect to an output. So, any fault generation algorithm you look into, so they basically do this thing. Somehow they need to excite the fault, so that we have to put the opposite of the stuck value at that point. So, that is the fault excitation, and we need to propagate the faulty response of that point to some primary output. So, these are the two things to be done by any ATPG algorithm. In many of the ATPG algorithms, so you will be using a 5-valued algebra instead of a two-valued logic. Okay. So, we will be using a 5-valued logic. So, what it does, what it helps is that we do not need to consider two copies of a circuit. So, previously we were telling that we need to have two copies of the circuit, a fault free circuit and a faulty circuit, and see whether their responses are different or not. So, instead of having two different circuits, so if we say that we have got only, we will work with only one circuit, then this 5-valued algebra is going to help us for doing the ATPG procedure without having multiple copies of the circuit. So, a signal value, we must be able to capture the fault free and faulty value simultaneously. So, this is the requirement. So, 0 or 1, so they are deterministic values, because they can tell a line to be permanently 0 or it's statically 0 or statically 1. On the other hand, so sometimes we need to tell that if this point is in a fault free circuit, if it is d, if it is some value, then in the faulty circuit it will be the reverse of that. So, this is captured by introducing two new symbols d and d bar. So, 0 1 x they remain as it is. So, 0 is static 0, 1 is static 1, x is unknown, and d and d bar. So, d may be, they can pick up the value 1 or 0. If so, d is picking up the value 1, then wherever in the circuit we have got d bar, so that will be equal to 0. And on the other hand, if d value at some point is 0, then all points that are d bar in the circuit, that are current logic assignment is d bar, they are at value 1. So, they are actually complementary, d and d bar are complementary to each other. By having this d and d bar symbol, so we can make our test generation process simple. So, if we just try to see how this algebra will work. Okay. So, we have got, say, one input is put onto this row, and another input is put onto this column. So, AND operation. So, if one of the input is 0, then naturally AND gate output is 0. So, there is no problem. If one of the input is 1, so AND gate output is equal to the other value. So, 0 1 d bar x. If one of the input is d, then other input is, so if d and 1 output is d and d is d, d and d bar is definitely 0, because they are complementary to each other. So, their AND must be equal to 0. Similarly, d bar and d, that is also equal to 0. Okay. Then d bar and d bar is d bar. So, like that we can formulate this AND table, and if one of the values is unknown and other one is not a definite controlling value, then the value will remain unknown. Okay. So, like these values they are remaining as unknowns. In an OR gate, so we can similarly formulate this logic table, and for NOT gate also we can formulate this logic table. So, it is we are showing it for only AND, OR and NOT. So, you can formulate several similar such tables for other logic functions like NAND, NOR, XOR. So, it does not matter. So, for all the logic families, so knowing that D and D bar are complementary of each other, so you can formulate this type of tables. Now, how a test generation process can work now? Okay. So, suppose that ATPG it systematically and implicitly searches the entire search space. So, this is my search space. So, first it will take up some variable, put it to value 0. After putting it to value 0, so it may find that next input is C. So, it puts the value C equal to 0, and in the process it explores the search space in this part where A equal to 0 and C equal to 0. So, this part of search space is this has got all solutions that are that can be obtained by setting A equal to 0 and C equal to 0. But it may so happen that for a particular fault, setting A equal to 0 and C equal to 0 does not lead to any test pattern. So, after a few steps in this tree, you will find that we cannot all the paths that are going further. So, they are not going to lead to any test pattern. There is no variable that can be set now to lead to the test pattern. So, in that case we can come back, we can backtrack and come with the other purpose. For example, suppose after some time we find that setting C equal to 0 is never going to lead to any test pattern set for a particular fault. So, we come back, try with C equal to 1. So, this way it can systematically search the entire space, solution space, and come up with the test patterns. So, these ATPG algorithms, they can systematically search the total solution space, and backtracking will definitely be required. As I was telling that if I find that D equal to A equal to 0, C equal to 1 and D equal to 0, after coming to this point we may find a situation that for a conflict has occurred. A conflict has occurred means there is no more D that is present in the circuit. So, we can set that D to 0 or 1, and so all D's have disappeared. So, the conflict has occurred and all the input values they got specified, and there are conflicting requirements for different paths for this excitation and propagation of this fault to the output. So, there is conflicts. So, we can say that this particular path is not going to lead to any test pattern. So, we come back, we do a backtracking, and then we come back here. Now, if we find that D equal to 1 also creates the problem, then there is also conflict, then we will try to explore the path which will come from here with C equal to 0. So, in this way this backtracking and this branch and bound, so they are going to help us in generating the test pattern set. Now, if you do not have any fan out in your circuit, then this can be a basic ATPG. So, fan out means that there is no branching, like if I have got some circuit here. So, these are the primary inputs, and after some time there is a gate, and this gate output goes to several places. So, we say that this is a fan out point. Now, if this type of situation is not there, then what you get essentially is a tree type of circuit. So, you have got some gates at the first level, then these inputs are coming there, then you have got some gate at the next level, then maybe some other gates after that, but it is never going to, but there is never going to be a fan out. So, if you do not have these fan outs, then we can very easily have a ATPG algorithm. So, it says that initialize circuit by setting all values to x. So, all input values, all these signal line values, they are set to x, and we are trying to detect this particular fault signal line G stuck at some value V. Okay. So, then we call justify fan out free, which is C, G and V bar. So, this will what it will try to do? It will try to excite the fault by justifying the line G to V bar. So, it will try to set the input values of the circuit such that this line G gets a value of V bar, and after that it will also the justification has been done. Now this V bar response has to be propagated to the output. So how can you do this? So there must be some propagation procedure. So this propagate Fanout-Free, so this CG, so this will propagate this line G to at least one of the primary outputs. Okay. So how can we do this justify Fanout-Free? So this algorithm is very simple. So start with G, set G is getting the value V. Now if it is primary input, then we are done. So if we are just trying to check for a if we are trying to justify a primary input to some value, so that is done, because the primary input can always be set to a value. Now otherwise, so if the gate type of G is AND gate, then if V equal to 1, then we need to justify all the inputs. So what we essentially mean, if this is the AND gate, so this is the line G I am talking about. Now so if this if we want to put this line to equal to 1, then all these lines are to be put to 1. So whatever input cone we have here for this for these inputs, so all of them, they need to be put to be equal to 1. So somehow ones must appear at all these points. So that's what is told here, that if gate type is AND gate, if the gate type is AND gate, then this if the value that we want to put is 1, then for all inputs H of G, we need to justify Fanout-Free CH1. So all the inputs are to be justified. Otherwise, if V is equal to 0, then we can very easily we can take only one of the inputs and put it to 0. So we pick up one input of G whose value is currently unknown. So we don't want to fall into any conflict. So we pick up some value of G, we pick up some input of G whose value is currently unknown and try to put a 0 there. And how can we put a 0 there? So we can call this routine justify Fanout-Free CH0. So it will put a 0 value at that particular point, at the point H. So this way it can continue. So this is a recursive routine, and this recursive routine, so if it finds after some time that we cannot proceed further, then it will pick up some other input and it will try out with that. So if we are trying with one input, it fails, so it can try with another input and do this thing. So similarly, for other gate type, if G is OR, then we have to just reverse this particular check, V equal to 1 and V equal to 0. In this way you can figure out, like all different types of gates, what has to be done. So once you know that your circuit is consisting of these types of gates, and if for each of them, so you can write down the corresponding code, so which will be doing this justification routine. So here suppose in this particular circuit, so we want to detect this fault G stuck at 0. So first it will try to call, it will try to justify, it will put a value, try to put a value of 1 at G. So it will justify Fanout-Free function will be called with the circuit C with the line G going to 1. So if this line G goes to 1, and then naturally it has to call, it has to put this 1 at both the inputs, because this is an AND gate. So it will call this justify Fanout-Free CA1. So since this is a primary input, so this will be immediately satisfied and A will be put to equal to 1. Now it will call this justify Fanout-Free F to be equal to 1, which, since this is an inverter, will recursively give a call to justify C stuck at 0. And then it will be doing this thing, that it will be putting this C to be, it is a primary input, so it will put C to be equal to 0. After that it will try to, so that is the justification of G. So this particular line can be set to up to a value. So G line can be set to 0. Next is the propagate routine. So in this example we have seen that how this G line can be set to 1. Now we need to propagate this G through this OR gate to this primary output. So that part will be done by this propagation routine. So if G has exactly one fan out, then we say, suppose H is the fan out of G. If none of the inputs of H has the value X, then backtrack. So this means we are trying to propagate, but there is only one fan out of G, that line is H, and the inputs of H are all none of the inputs of H are X, that is all the inputs of H are already specified. So, we cannot do anything. Okay. So, then it will be then we need to backtrack, because through this line H we are unable to send the output, send this line G to the output. Otherwise, G has more than one output. So, if G has more than one output, more than one fan out, then it will pick up any one fan out of G that is unjustified. So, it is not yet taken care of. So, it will pick it up. Now, it will try to propagate this G through this H. So, this H is AND gate, and then for all inputs J of H such that J is not equal to G, if the value on J is X, then it will try to propagate. So, it is basically I have got say this line has to be propagated. Now, we see that this line, so this is the line H that we want to propagate. So, it is coming from this AND gate, this line G. So, it has got many fan outs. So, out of that this fan out has been chosen. Now, it will try to see that other inputs of H, other inputs of this AND gate, they need to be justified, so that we can this H propagate. So, at present what is required is all these values must be at X. Okay. So, all so if the value is on the value of J is equal to X, then we need to put the value to be equal to 1. So, Cj1, that has to be done. Similarly, if the type of the gate is OR gate, so it is just the reverse logic. So, if we need to put this J equal to wherever we have got J equal to X, we need to put the J equal to 0. In this way, for all the gates, all types of gates, we can write down the routine, so that it will propagate through the circuit, that the line G will propagate to the primary output. We will continue in the next class.